Let us now discuss about symmetric and antisymmetric FIR filters. In order for an FIR filter to exhibit linear phase, the necessary and sufficient condition to be satisfied is that the impulse response h of n must have a finite duration, capital N, and it should exhibit either symmetric or antisymmetric about the midpoint. Mathematically, we can describe symmetry as h of n is equal to h of capital N minus 1 minus n. The representation on the right is nothing but h of n taken in reverse. As we know, n minus 1 is the index of the last point in an n-point sequence, since indexing starts from 0. Now, if h of n is same as h of n minus 1 minus n, it is said to be symmetric. The condition called as antisymmetry is when h of n is equal to negative of h of n minus 1 minus n for the same values of n between 0 to n minus 1. Let us talk about the condition called as symmetry first. If you see the plot of impulse response, we have two cases. First, when the impulse response h of n is even, the length of n is even, it's an even number. In the second case, the h of n, if its length n is odd, when we say n is even, we are showing the points for h of n which starts from 0 till n minus 1. We are aware that n minus 1 by 2 is the midpoint. So at the center here we have the midpoint. If n is an even number, then the last point here will be odd. If n is even, n minus 1 is an odd number. For example, if n is 8, then n minus 1 will be 7. Then the midpoint, n minus 1 by 2, becomes 3.5. And we are aware that values are found only at integer values. So 3.5 being the midpoint, we cannot have a value here. Therefore, we conclude that whenever the value of n is even, the midpoint n minus 1 by 2 does not carry any value. Now, the values are found on either side of the midpoint. To compute these values of the index, we can perform a very simple exercise. So, if we take the midpoint, that is n minus 1 by 2, now since we are in the middle, this entire thing is 1 unit or 1 increment. Okay, so we are in the center. So if you're going back, we should cover half a step. Therefore, if I want to calculate the previous value, I can subtract it by 1 by 2. This is half a unit. The entire thing is 1 unit, so half a unit. So I'm decrementing or subtracting minus 1 by 2. And the result you will get here after subtracting this will be n minus 2 by 2, which can be written as n by 2 minus 1. So the index, which is the previous point before the midpoint, is n by 2 minus 1. Same way, if we are going forward by half a unit, so this is the midpoint, n minus 1 by 2. If we are going forward half a unit, we end up with n minus 1 plus 1, that is equal to n divided by 2. So the next point where we have the value is n by 2. So it is very simple to arrive at the index for the points on either side of the midpoint. Let us now move to the case when n is odd. Now when the n is odd, the n minus 1 will be even and n minus 1 by 2 will also be even. So the value at this midpoint will definitely have a result there. You will have a value found at the midpoint. Therefore, we can easily identify that the midpoint carries a value in the case of n being odd, and the points which are on either side of the midpoint can be very conveniently calculated by adding 1 and subtracting 1. So when you take n minus 1 by 2, subtract 1 from it, the simplification is n minus 1 minus 2 divided by 2. This is nothing but n minus 3 by 2. So we get n minus 3 by 2. Similarly, when you're moving one step forward, we have to add 1. The index is going to increment by 1. Therefore, n minus 1 by 2 being the midpoint, so midpoint plus 1 simplifies to n minus 1 plus 2 divided by 2, which is equal to n plus 1 by 2. So in this manner, very easily we can find out which are the index required in the case of both even as well as odd. Let us first consider that the impulse response h of n is symmetric and the length of n, the size of n, is even. This is a transform of a causal finite duration sequence h of n where n value is between 0 to n minus 1. So it's an n point sequence. Definitely it is finite. It lies on the right hand side, 0 to n minus 1. It is causal. Now, Z transform, as we are aware, is given by, from the definition, x of z is equal to summation n lies between minus infinity to plus infinity, x of n z power of minus n, where z is a complex exponent. Now, since the input x of n here is equal to h of n, therefore, we can replace x of n by h of n in the summation. And the limits are changed to n between 0 to n minus 1 because that is where the value of h of n is found. So this equation is called as equation 1. Now, for n even, this above summation could be broken into two summations of equal size. So each summation will comprise of n by 2 points. So as we have learned from our previous discussion that n will have an index from 0 to n by 2 minus 1. So this depicts the left half. Similarly, the next set of points will have the index n is equal to n by 2 to n minus 1. This will be the right half. Now, we are aware of the condition which is called as symmetry. The symmetry condition has taught us that h of n is equal to h of capital N minus 1 minus n. Now we want to introduce this sort of index in this equation's second term. To do that, let us create a term which is called as m. Now this m value is equal to capital N minus 1 minus n. So this has to be inserted in the second summation. Now in the second summation we have a term called as n. Therefore, from this equation, n could be expressed as capital N minus 1 minus n. Now since n is being replaced, we have to change the limits as well. The limits can be calculated by substituting the values of the previous limits in the equation. Therefore, substituting n is equal to n by 2 in the equation for m and simplifying it gives you the limit n by 2 minus 1. Substituting the upper limit, which is n minus 1, capital N minus 1, in the same equation and simplifying gives you the limit which is 0. Therefore, now equation 2, second summation, will become what is shown here. The first term is untouched. The second summation will now carry the limit in terms of m. The lower limit is n by 2 minus 1. The upper limit is 0. And here, the index of h has now changed. It has become n minus 1 minus n. Similarly, the power of z is minus of capital N minus 1 minus m. So both places we have replaced the value for n. Now, since we are performing summation, it doesn't matter in what manner we are adding. Therefore, we can just interchange the limits. We are just interchanging the limit. So the upper limit 0, we now call it as a lower limit. The upper limit is n by 2 minus 1. Because we don't care how we add. We can add from left to right or right to left. The answer will always be same. So this equation can be called as equation number 3. Now since m here is a dummy variable, we can actually change it. You can call it by any name. So we replace it by n. Instead of calling it as m, we call it as n. Then the equation changes slightly again. The index is now called as n, and here we have changed that m to n, and here also we have changed that m to n. This equation will be called as 4. Now we remember the condition which we call as symmetry. Now from symmetry we have learned that the value of h of n is same as h of capital N minus 1 minus n for n ranging from 0 to n minus 1. Therefore, we can replace it with h of n. Next, when you replace it with h of n, now we see that both the summations will have the same limits. It has the same common h of n as the term. So we gather all the common terms, that is, we keep the limits common, we have h of n which is common, and the terms which are not common are written here in bracket. From the first summation we get z power of minus n, from the second summation we get z power of minus capital N minus 1 minus n. Okay. Then after this stage we want to obtain the frequency response of the digital filter. Now this is possible by allowing z value to become e power of j omega. So substituting z is equal to e power of j omega in the above equation. So we find the term z and we change it to e power of j omega. So first we have h of z, that will become h of e power of j omega. Next we have the z term here as well as here. Both of them will be replaced with e power of j omega. Now after making the necessary substitutions, we can observe that the equation has now become h of e power of j omega, which can be denoted as h of omega also. This is equal to summation n between 0 to n by 2 minus 1 h of n. In place of z we have put e power of j omega. Therefore it becomes e power of minus j omega n plus e power of minus j omega into n minus 1 minus n. Further, in the next step, we want to perform the simplification. The simplification is possible by taking out a term which is e power of minus j omega times n minus 1 by 2. Please remember, n minus 1 by 2 is a midpoint for the impulse response. So, if I want to take this exponent out of the first term, we can compensate by inserting the same value and removing the same value. That means that in the term which is outside, if we have a negative sign, we should have a same exponent here with a plus sign. So we can observe here we have e power of minus j omega n, which was originally a part of the equation, and we have an extra term which is e power of minus into minus, that is plus j omega times n minus 1 by 2. So we have compensated for it by adding and subtracting a quantity with the same exponent power, but the sign is opposite. Similarly, for the second term also, since we have minus here, there we should have a term with plus j omega. So therefore, we can observe that after simplifying, you get an index here which is n minus 1 by 2. Then we divide the whole expression by 2 and we multiply by 2. This is an attempt to write this equation in the form of cos, because we know cos theta is e power of j theta plus e power of minus j theta divided by 2. Therefore, now the equation could be written as, the equation takes the form of e power of minus j omega n minus 1 by 2 is outside the summation. Within the summation, limits are n is equal to 0 to n by 2 minus 1, 2 times h of n cos of omega times n minus capital N minus 1 by 2. So n is the index that we normally use in time domain for the impulse response h of n. Capital N minus 1 by 2 is the midpoint. Omega is the frequency. So we have to remember this particular expression so that we can compute the frequency response for FIR filter. And this is applicable for the case when capital N, the length of the impulse response, is even. So this result in equation 5 is an important one. Next, to prove that this is linear, we compare equation 5 with h of omega, which is expressed as hr of omega. R stands for real. hr of omega is a real function of omega. Now, this is multiplied with e power of j theta omega, where theta of omega will be the phase. So hr of omega is the amplitude and theta of omega is the phase. Now, hr of omega, as we said, is real function. It's a quantity which is indicated by the summation here. We can see no j terms here. The conclusion, it is definitely real. Whereas the exponent is the term which is beside j here. Therefore, the exponent power is theta k, which is equal to minus omega n minus 1 by 2. Therefore, now we can express the hr of omega is the summation as shown. It is summation n from 0 to n by 2 minus 1, 2 times h of n cos of omega times n minus capital N minus 1 by 2 within the brackets. And theta of k, which is the phase, is given by minus of omega n minus 1 by 2 for the magnitude of hr of omega more than 0, and if it is less than 0 or it is negative, then we have to add an extra pi here. Now from this relationship for the phase, we clearly observe that these relations are linear. Hence, we have proved the fact that if you are able to have a condition that h of n is symmetric about its midpoint, then you will get a linear phase response. Let us now consider the case when we are discussing the condition called as symmetry and we are taking capital N to be length odd. Once again, h of z is given by summation n is equal to 0 to n minus 1. H of n is the impulse response into z power of minus n. This comes from the definition of Z transform. Now this h of z can be split into 3 parts. Whenever the n is odd, we have learned that the center element, that is n minus 1 by 2, will carry a value. And then we'll have values on either side of the midpoint. So we have a left part, we have a right part, and we have a center element. Therefore, the 3 terms can be described. So starting from the left, the index starts from 0 till n minus 3 by 2. The quantity inside the summation is the same for the left and right half. Next, we have the center element. The center element is situated for index n, which is equal to n minus 1 by 2. Therefore, putting n as that particular value, we get the term h of n minus 1 by 2 z power of minus n minus 1 by 2. This is a single term. Once again, for the right half, we have the index which starts from n plus 1 by 2 till n minus 1, and the summation quantity is same as the first term. So this equation is called as equation number 2. Now, similar to the last method, where the second summation we tried to insert the value in place of n. So here also, let us put m is equal to capital N minus 1 minus n. Using this, we want to change the value of the index called as n in the third term. So this is quite similar to the previous solved example. Now, after doing the manipulation, we can observe that the third term will now become h of n minus 1 minus m, z raised to minus n minus 1 minus m, and the index after calculation will be m is equal to n minus 3 by 2 and upper limit will be 0. We are aware that since m is a dummy variable, we can change it or replace it with n, and we can also interchange the order of summation. Therefore, after doing both, the third summation now becomes n is equal to 0 to n minus 3 by 2, and here we have changed m to n, and here also m is changed to n. So these are the changes we have made. Now we have the three summations as shown here. Now let us make use of the symmetry condition. We are aware that h of n minus 1 minus n is same as h of n. Hence replacing and collecting the common terms in the first and third summations, you can express it now as summation n from 0 to n minus 3 by 2, the limits, h of n into z power of minus n plus z power of minus n minus 1 minus n. Please note this looks very much like the term we had for n even, with the difference that the limit, upper limit there was n by 2 minus 1, here it is n minus 3 by 2, for odd it is n minus 3 by 2. And we should not forget that there was a midpoint term which is given by h of n minus 1 by 2, z power of minus n minus 1 by 2. So the three summations, two are combined, but the center element term is kept as it is. Next, we obtain the frequency response by replacing z with e power of j omega. Now this produces the equation as shown, h of e power of j omega, which is same as h of omega, is equal to, here is the midpoint term, we have changed z, so it becomes e power of minus j omega raised to n minus 1 by 2. And the summation, here we had two z terms which are now replaced with e power of minus j omega n plus e power of minus j omega n minus 1 minus n. So as we had discussed, the nature of the summation is same as the previous, so the method of simplifying is also quite similar. So once again here, we take out the term which is e power of minus j omega times n minus 1 by 2 outside the summation, and inside we get the exponent to be expressed like this. Further, we divide by 2 and multiply by 2 so that we can express the quantity inside the square bracket as cos theta. Therefore, the result after replacement becomes, taking common, because all the terms have this exponent, we take it common, e power of minus j omega n minus 1 by 2 is common. The first term gives you h of n minus 1 by 2, this is the midpoint index, plus summation n from 0 to n minus 3 by 2 upper limit for n odd, 2 times h of n cos of omega small n minus capital N minus 1 by 2. This summation is same as that for the even case. So this is quite simple to remember if you practice it. Now we know in this above equation we can express it as hr of omega into e power of j theta omega. hr of omega is the real function of omega. Then hr of omega is equal to h of n minus 1 by 2 plus the quantity inside the bracket, it's a whole quantity inside the bracket, h of n minus 1 by 2 plus the summation with the cos term. And theta of k is identical to what we got in the previous case. It is minus omega n minus 1 by 2 and minus omega n minus 1 by 2 plus pi when hr of omega is greater than 0 and when hr of omega is less than 0. So it's the same result as the previous, and this also proves that when n is odd, if you maintain symmetry condition, then you obtain linear phase. Similar derivations may be carried out for antisymmetry condition also. Thank you all.